He was born in Bremen, Germany, at the end of the first decade of the 20th century, and emigrated to Texas with his family when he was 7 years old. He was a good student, and after graduating from Texas A&M University in 1931 with a degree in science, he joined the Army and became a bomber pilot. He went on to further his education with advanced degrees in aeronautical engineering. After World War II, his interest in aeronautics blossomed and led to a career in the scientific and research field. He directed both the development of the ballistic missile program and the Air Force's initial space program, and did it all in a very short span of years.
I'd not only consider Schriever a visionary, I'd have to say that he might have been the preeminent visionary in terms of what the Air Force has become.
His name is Bernard A. Schriever, and he is a legend of air power. He was born Bernard Adolph Schriever in Bremen, Germany on September 14, 1910. His father, Adolph, worked as ship's engineer for the North German Lloyd steamship line and was interned when his ship was seized in New York in 1916. Shortly after that internment, Bernard, his younger brother Gerhard, and their mother Elizabeth joined him in the United States, and they settled in San Antonio, Texas. Unfortunately, tragedy struck in September 1918 when his father was killed in an industrial accident. So at a tender age, young Benny became the man of the house. As with many immigrants, the family faced hard times, but persevered. His mother worked as a housekeeper and sold sandwiches and cold drinks to golfers at Breckenridge Park Golf Course. Benny and his brother helped the family finances by doing chores and caddying. The Schrievers stuck together, worked hard, and became naturalized citizens. Benny excelled in school and graduated with honors from San Antonio High School. In 1931, he graduated from Texas A&M University with a Bachelor of Science degree in architectural engineering. Shortly after graduation, he accepted a reserve appointment in the field artillery, but found he was much more interested in aviation. He entered flight training at Randolph Field, Texas in June 1932, earned his wings, and was commissioned a second lieutenant in the Air Corps Reserve at Calif, Texas the following June. From Calif, Second Lieutenant Schriever was assigned to bombers, and over the next 4 years was stationed at March Field and Hamilton Field, both in California.
I can remember at March Field, we had a poker game going. We had about 10 players. We didn't, all 10, of course, didn't play at one time, but we usually played once a week, but often not quite that frequently. But who were playing in the game? We had Tui Spots, we had R. Aker, we had Clarence Tinker, and we had a group of lieutenants. I mean, you wouldn't have that sort of thing today, I don't think.
His active duty ended in mid-1935, and he was hired as the commander of Civilian Conservation Corps camps in New Mexico. In October 1936, he returned to active duty and was assigned to Albrook Field, Panama, where he was aide to the commanding general, Brigadier General George H. Brett. It was also at Albrook where he met his future wife, General Brett's daughter, Dora. In September 1937, First Lieutenant Schriever reverted into the inactive reserve to take a commercial pilot position with Northwest Airlines.
I guess that's the only time I ever played golf with Hap Arnold. When I was flying for Northwest Airlines, he flew into Seattle, that's where I was based, for a meeting with Bill Allen, who was the president and CEO of Boeing Aircraft. And he asked Bill Allen, would he arrange a golf game while he was there, and if Benny Schriever is available, how about getting him in the foursome? And it worked out that way. I was available, and we played 18 holes of golf at the Seattle Country Club. And Arnold said, this is a true statement and shows you the kind of vision this man had. He said, look, I want to get every Air Force officer, Air Corps officer, been flying on the airlines back into the regular Air Force. because I want an all-weather Air Force. His vision was such that we had essentially an all-weather Air Force in World War II.
He re-entered the regular Army Air Corps in October 1938 as a second lieutenant and was again stationed at Hamilton Field, California, where he was assigned to the 7th Bomb Group as a B-18 instrument flying instructor. A year later, the Schrievers moved to Wright Field, Ohio, where Lieutenant Schriever was assigned as a test pilot. While at Wright Field, he attended the Air Corps Engineering School, specializing in aeronautical engineering subjects, and graduated in July 1941. Upon graduation, the Schrievers went back to California, this time to attend Stanford University, where he earned his master's degree in mechanical engineering, aeronautical, and while a student at Stanford, he was promoted to captain. By now, World War II was in full swing, and Captain Schriever was immediately sent to the 19th Bomb Group in the Southwest Pacific. While in the theater, he flew 38 combat missions in B-17s and other aircraft while serving as the group's chief of maintenance. He was only a captain for 3 months. In January 1943, his meteoric career began in earnest, and by war's end, he was a full colonel and commander of the advanced headquarters of the Far East Air Force Service Command, where he directed all combat support functions for theater operations from bases in New Guinea, the Philippines, and Okinawa. With the war finally over, Colonel Schriever was brought back to the United States and became chief of the Scientific Liaison Section in the Office of the Deputy Chief of Staff for Materiel in the Pentagon. While in this office, the young colonel was fortunate to work closely with the legendary Dr. Theodore von Karman, head of the Scientific Advisory Board. Von Karman took Schriever under his wing, introduced him to many leading scientists.
Von Karman, von Neumann, Edward Teller, and so forth were very. I developed very close relationships with all of those people during that period, from 1945 until 1950 or 49, late 49, when I went into National War College, and then the Development Planning Office, right out of the War College back to the Pentagon again.
It was here that he devised a revolutionary method of analysis called Development Planning Objectives, or DPOs. The DPOs helped identify promising advances in technology and coordinated these advances to meet future operational requirements of the Air Force.
General Schriever was the right man at the right time to give us two things: a strategic, long-range rocket deterrent against the Soviet Union, and secondly, the capability to orbit the first Americans in space. And when we look at the work of General Schriever in the 1950s in building the ICBM force, we see here that Schriever draws on some of these projects, Toward New Horizons, a long-range forecasting project of the late 1940s. He draws upon some of the work that's taking place in the physics community to reduce the size and weight of nuclear warheads, and he puts this together to give us the nuclear-tipped ICBM.
The other person who's very important in this discussion is Trevor Gardner, who was the assistant to the Secretary of the Air Force. And he's the one who put Schriever in a position to realize the development of these weapons. Gardner and Schriever then set up a Teapot Committee, which was headed by von Neumann, and they handpicked the members of that committee. And they concluded that if a crash effort were undertaken outside the normal channels of the Air Force, that was free of institutional bias, then they could do that. And Schriever was in it every step of that way. And incidentally, Ramo and Wooldridge, Simon Ramo and Dean Wooldridge, who were young scientists who'd worked for Hughes Aircraft and developed missiles for them, were also in on this committee, members of the committee. So a lot of this was cooked early on in the Eisenhower administration. The irony of it is that the Eisenhower administration came in with a program to cut the missile program, but then when they saw what the potential was of this thing, and they were supported enthusiastically by Schriever and Trevor Gardner and John von Neumann. Then the Eisenhower administration decided that this was the way to go to get more bang for the buck, in the words of Charlie Wilson, who was the Secretary of Defense, that development of ballistic missiles was something that would certainly help in the Cold War.
Gardner asked Schriever to take over the program. Schriever agreed, but only if he could have full authority to get the job done. By now, Schriever was a new brigadier general and was named assistant to the commander, Air Research and Development Command, in June 1954. 2 months later, the Western Development Division was created in Inglewood, California, and Schriever was named its commander. The assignment officially put him in the driver's seat to manage the ICBM program. Schriever proposed that the best way to proceed was to create a government-industry partnership. He prevailed, and in short order, 2 partnerships were formed to make the difference in the race for the ICBM. The partnership of Simon Ramo and Dean Wooldridge joined to create the Ramo-Wooldridge Corporation. At the same time, Schriever and Simon Ramo, who was chief scientist on the ICBM program, adopted yet another partnership.
At about the same time that the Ramo-Wooldridge Corporation began, the intelligence community decided that the Soviet Union was a real threat in creating an ICBM that would bypass the entire multi-billion-dollar defense system of the United States. And the ICBM program immediately became the #1 crash program.
Thrust at the center of a highly secret crash program, a program that was considered by many experts twice as complex as the Manhattan Project, Schriever, Wooldridge, and Ramo tapped into all the nation's technological resources, recruited the best and brightest from universities, government, and over 220 major companies. To maintain secrecy, now Major General Schriever and his Air Force team wore civilian clothes to work and operated out of the Ramo-Wooldridge facilities. Besides the urgent threat they were laboring against on national security grounds, the government industry team gave birth to the systems engineering and electronics that later spawned the field of space technology. For their advances, Wooldridge, Ramo, and Schriever all gained celebrity status in Time magazine in 1957.
Messrs. Thompson, Ramo, and Wooldridge worked extremely effectively with Schriever in terms of supporting the development of the ICBM force, and then going beyond this to support the development of satellite payloads, particularly early satellite reconnaissance payloads and military payloads for national security purposes.
In the area of weapons acquisition, Schriever and Ramo fashioned a new approach to systems engineering. For reasons of time and speed, they took what Ramo called a parallel approach, or working on all subsystems at once. Later known as concurrency, it was a very risky approach, but it paid off. To succeed, breakthroughs had to be achieved in missile guidance, missile structure, propulsion, flight control, and nuclear warhead weight, all at once. But just as the ICBM program began to take shape, the Department of Defense implemented cost-cutting measures which threatened the pace of the project. But the measures were quickly dropped after the Soviets launched Sputnik in October 1957, shocking the defense community and nation and adding a new sense of urgency to the ICBM program.
We had failures in the early days on all of our missiles, every one of them. The Atlas, the Titan, the Thor. The Minuteman was a success on the very first flight, all up. But that was, again, because we had a great deal of pressure on, and we took the risk of doing all 3 stages, the guidance, and the whole works.
Ultimately, the United States succeeded, and in the 1960s surpassed the Soviet Union and won the race for an operational ICBM and, as a byproduct, the space race. At the heart of these achievements were the government-industry partnerships conceived by General Schriever and exemplified by the teamwork of Schriever, Simon Ramo, and Dean Wooldridge. General Schriever's achievements over a relatively brief span as head of the ballistic missile programs included the development of a new class of weapon systems, a second generation on the way, and the frontiers of space well marked.
Roger, I understand our copy. He is outside of the space time at this time. I don't know, we're coming over the west end. I want you to come back in now.
In April 1959, Benny Schriever was promoted to Lieutenant General and named commander of the Air Research and Development Command. His command was vast, and he was now responsible for managing the widespread military, science, industry brainpower required to provide the Air Force with the military tools to do its job. To get the job done his way, General Schriever introduced his concept of concurrency to weapon system development and acquisition, the same concept that had worked so well for him at the Western Development Division.
This method of management certainly was not a happy thing for the assistant secretary's level, because we came in with a program every year and presented it to the Pentagon, and we didn't have any problems. We kept them informed, but we didn't have anybody that if he couldn't say yes, he couldn't say no. In other words, that in essence is what happened.
As before, he wanted complete control over the development and acquisition process. But he faced fierce opposition from the Air Material Command Commander, General Samuel Anderson, whose command controlled weapon systems production. Although the Air Staff in the Pentagon offered many compromise positions, none was accepted, and the disagreement went on for 2 years. The deadlock was broken when the Air Force was given the opportunity to be assigned full responsibility for all military space programs, but on the condition that it solve the split between Air Research and Development Command and Air Material Command. The Air Force Chief of Staff, General Thomas D. White, wasted no time in deciding in favor of Schriever when he established 2 new commands, Air Force Systems Command and Air Force Logistic Command. Schriever was promoted to 4-star general and made the first commander of the new Air Force Systems Command. He reached the goal of total control and was now responsible for research, development, procurement, and production actions required to place a complete aerospace system in operational use. Although General Schriever had reached the goal he sought for so long, the administration changed, and the philosophies of the Eisenhower administration were not shared by the Kennedy and Johnson administrations with regard to the pursuit of technological advances.
It's true that he was very frustrated with the McNamara administration's cancellation of many of the military programs. But the thing that really irritated Schriever was not so much the cancellation of those programs. That he could accept. I mean, that was within the purview of the Secretary of Defense. The thing that really irritated Schriever about McNamara's opus operandi was that he would do this without debate. There was no public debate. There was no institutional debate. It seemed as if this was just done unilaterally.
Schriever saw all the streamlining of weapon system development and acquisition that he enjoyed during the development of the ballistic missiles replaced once again with layers of review, or as he called it, paralysis by analysis.
Beyond this, General Schriever, of course, as head of Air Force Systems Command, was responsible for a very important long-range planning effort, Project Forecast. And Project Forecast and some of the spin-off efforts of Project Forecast brought to this country some tremendous things as well, one of which was the high-capacity, long-range global jet airlifter and the high bypass ratio turbofan engine. Basically, when we take a look at the modern air transport era, we see there, too, the legacy of some of the work of this remarkable man.
We had scientific community, we had industry, and we had military all involved in the Project Forecast. It would be very difficult to make such a study today because of conflict of interest problems. And I think it was a very good study.
General Schriever found the administration's defense policy of mutually assured destruction, which meant the United States would fix its numbers of strategic weapons in the belief the Soviet Union would do the same, as foolhardy. He also thought the autocratic rule of Secretary McNamara irksome, and he could no longer support the administration's defense policy. Thus, he voluntarily retired on August 31st, 1966, several years before his mandatory retirement date. Since his retirement, General Schriever has been in great demand as a consultant to civilian organizations looking to solve problems through systems engineering. He is also still a frequent unpaid advisor to the Air Force and Department of Defense.
We're not really moving fast enough as far as space is concerned. We still are living with that space business which says space for peaceful purposes. And in my book, the military is here for peaceful purposes, to keep the peace. We don't want to fight a damn war unless we're forced into it. And one way to keep the peace is to have a credible capability that these guys do not want to mess around with.
Although the name Falcon Air Force Base will always have a cherished place in the heart of aerospace warriors, it's fitting that we honor an American pioneer, a living legend, whose lifelong work made what we do in today's Missile and Space Force possible.
On June 5th, 1998, the Air Force Space Command's Falcon Air Force Base, Colorado, became Schriever Air Force Base, renamed in honor of General Bernard A. Schriever, the father of the ballistic missile and the Air Force's space program, a tribute rarely accorded a living person.
If one looks for the legacy of General Schriever today, all one has to do is go to the Cape or go to Vandenberg Air Force Base, because every time a military payload is put into orbit, every time a missile system leaves a launch pad, every time a commercial payload is placed in orbit, we are seeing there the legacy of General Schriever.
General Bernard A. Schriever was born in Germany, immigrated to America when he was 7, and rose to become a great American patriot. He had a long and distinguished career in the United States Air Force, and as the father of America's space program, is a true legend of air power.
Let's assume your crew is assigned sortie number 8 of your unit's emergency war order. You were launched under positive control some 2 hours ago, and the closing rate to your assigned target is 7 miles every minute. You don't know whether this is the real thing or not. You won't know until you've reached your go, no-go position. The technical details of your air crew duties are second nature to you. You know your business, and through past experience, you know that every detail in your combat mission folder, the routes, refueling areas, turn points, IPs, and delivery tactics, has been carefully planned and cross-checked by the most highly qualified staff of combat planners available. In the mission planning stages, your particular sortie has been flown and reflown. IBM computers have been freely utilized to feed adverse planning factors into your sortie, cranking in varied power settings, worst wind factors, loss of engines or power, as well as high and low delivery components. In all this, the planners aim to assure you the best fuel pad and time-distance separation obtainable from weapon effects. You, yourself, have flown profile missions over and over again on USCMs and ORIs, and you know that the missions, whether high level or low, can be successfully accomplished as indicated in the tactical doctrine. But there is one area in which you've had little or no actual experience: nuclear effects. So it is understandable if there is an air of uncertainty about it in the back of your mind. In reality, an abundance of experience on nuclear effects has been accumulated over the past 14 years. Hundreds of men have flown nuclear test missions in conjunction with detonations of high yield and low, both in the Pacific and Nevada test operations. This experience has been funneled to your combat mission planners, so that your route beyond the H-hour control line, commonly referred to as the HHCL, can be planned with maximum safety. These nuclear effects criteria have as much, if not more, influence on your role in the emergency war order than any other operational factor. This phase of planning is particularly vital in today's multi-bomb raids, when your route must be plotted to avoid not only the effects of the weapons you release, but all weapons dropped in your general area by adjacent strike forces. All planning computations are carefully refigured and cross-checked by the planning staffs of your wing, numbered Air Force, and SAC headquarters. Equally valuable is the continuous scrutiny you and your fellow crewmen give to your own assigned sortie in relation to adjacent missions. The combat mission planners know there is no minimizing the awesome nature of this nuclear force, nor the extent of its effects. Here is a general refresher on each of these effects: thermal, blast, and radiation, presented in their relationship to your aircraft. Thermal, the light and heat hazard, radiates from the detonation in two phases. The first phase is instantaneous, comprising only 1% of the total thermal effect. Yet, it is this phase of the pulse, occurring quicker than the normal blink reflex of the human eye, which is responsible for flash blindness. You must be about 80 nautical miles away to avoid even minor flash blindness when looking directly at the detonation. However, your thermal curtains keep out all but a minor portion of the light. The second phase of the thermal pulse is long and cumulative, with the heat energy building up on the aircraft like a hand held too long above a match. Whenever there is new snow on the ground or clouds above the flight level, some additional thermal effect is received. However, the aircraft skin, coated with white paint, reflects most of the heat, and the airflow over these surfaces further reduces the total heat absorbed. Also, the thermal curtains can withstand tremendous heat, almost twice the amount anticipated. After the thermal hot foot has passed, the shock wave arrives with its twofold effect of overpressure and gust. Overpressure, the sharp increase in pressure, consists of successive positive and negative phases which produce a wraparound crushing action. Overpressure is the dominating effect at low altitude, with the vulnerable structural parts of the aircraft being the bomb bay doors, radomes, and access panels. Gust is usually the dominating effect at high and medium altitudes. Gust loading, similar to atmospheric turbulence, gives your aircraft a sharp jolt as it builds up on the lifting surfaces of the wing and horizontal stabilizer. Nuclear radiation consists of instantaneous bombardment of gamma, neutron, alpha and beta rays, followed by radiation particles in the nuclear cloud, which later becomes fallout. Instantaneous radiation can be dismissed because of your distance from the burst. Fallout is a ground problem. As an air crewman, you need only be concerned with the nuclear cloud and the safe separation times given you by the EWO planners. This will be discussed later. In concluding this general rundown on nuclear effects, here is a representative chart showing the limiting envelopes of radiation and thermal compared to those of overpressure and gusts. It took years of actual testing, millions of dollars, and a wealth of scientific and technological know-how to determine these envelopes on which your safe separation times and distances, as well as delivery tactics, are based. Shortly after the Hiroshima and Nagasaki results expanded concepts of warfare into atomic dimensions, men from the armed services, the Atomic Energy Commission, and scores of scientific laboratories began trooping out to the Marshall Islands in the Central Pacific and to the desert wastes of Nevada for periodic nuclear weapon tests and weapon effects operations. Our interest concerns the effects testing, particularly the vast amount of time and effort devoted to gaining effects information on aircraft structures, from the Crossroads operation all the way to the hardtack effort. On Crossroads, a modest beginning was made when the Navy placed instrumented aircraft and separate components aboard its test ships in Bikini Lagoon. The kiloton yield Able and Baker shots provided only a smattering of blast and nuclear radiation data. (1950). Operation Greenhouse, Eniwetok Atoll. Besides instrumented aircraft components set out on the islands in the vicinity of several kiloton size bursts, instrumented drones skirted the burst area to gather blast and thermal data. While preparations were made for the next test operation, the Massachusetts Institute of Technology utilized the Crossroads and Greenhouse findings to begin developing the concept on which the current SAC effects doctrine is based. 1952, Operation Ivy, Eniwetok Atoll. The first thermonuclear detonation, known as the Mike shot, was achieved. Mike was a liquid fuel experiment, but its success proved out the fusion principle, paving the way for the equally successful dry material version, patterned for more practical weapon utilization. On Ivy, instrumented B-47 aircraft were sent aloft to be tested at 50% of thermal design. B-36s were tested for both thermal and gust loads, also at approximately 50% of design. 1953, Operation Upshot Knothole, Nevada, again featured kiloton yield bursts. In addition to B-36 and B-50 aerial testing, ground tests were conducted on aircraft of several types, exposing them in various orientations to surface and air bursts at graduated overpressure levels, many beyond the breaking point. The aim was to verify laboratory tests and analyses concerning failure modes on aircraft through overpressure and gust effects. (1954), Operation Castle, Marshall Islands, involved aerial participation in megaton-size events by B-47s and B-36s. These aircraft, like those in all operations, were extensively instrumented by the Wright Air Development Center. For the B-47 test aircraft, interest centered on the effects of radiant heat on the aluminum skin of the ailerons. Thermocouples mounted at selected points in the skin and supporting structure gave temperature readings, while radiometers and calorimeters in the fuselage gave thermal time history and total input. A variety of blast gauges and cameras mounted under the fuselage aimed at zero to assist orientation calculations, completed the array. On 5 successive pre-dawn shots, the B-47 flight pattern at 35,000 feet was selected to position the aircraft where its aileron skin would receive the maximum allowable temperature rise to 370 degrees. In all instances, the maximum skin temperature rise was substantially lower than predicted. Heat damage in all cases was minor, involving only some patches of blistered paint at various points. The highest overpressure recorded on these 5 missions was around 1/3 of a pound. 1955, Operation Teapot, Nevada. Teapot's most ambitious aircraft structures test involved 3 F-80 drones to investigate lethal blast effects at shock arrival time from a 22-kiloton tower shot. Each drone was completely instrumented for loading input and structural response data to check laboratory analytical predictions. Test results were obtained by telemetering the data to ground stations. The aircraft were positioned directly overhead at altitudes of 3,800, 4,300, and 5,100 feet. At the burst, high-speed cameras under the canopy recorded the crucial seconds of impact. The wingtip instrument pods of the lowest F-80, only 3,800 feet above the burst, were blown off with a shock wave. As this drone was being shepherded back to a landing, radio control was lost, and it crashed. The other 2 drones suffered relatively minor damage. The middle drone was brought in without incident, while the top aircraft's nose wheel collapsed after landing, resulting in the drone's pileup at the end of the runway. The results of the F-80 test had important application to in-flight blast response for all types of aircraft. Also on Teapot, this array of vertical stabilizers placed close to the burst provided information on structural response under gust loading. (1956), Operation Red Wing in the Marshall Islands featured structural testing on a variety of aircraft, including the B-52 and B-47. The latter aircraft was oriented side-on to detonations for the first time. One heavy bomber project on Red Wing was concerned with the effect of gust and overpressure on an aircraft structure just after it had been heated by thermal. During these tests, thermal loads as high as 200% of design were recorded, along with gust loads which ran between 95% and 115% of design. These tests raised thermal design limits to 600 degrees Fahrenheit for the B-52 and 500 degrees for the B-47. Throughout the years, on selected weapons test operations, SAC aircraft and crews participated to refine operational procedures. Perhaps the most significant was the IBDA project on Operation Red Wing, where SAC crews of the 301st Bomb Wing flew simulated delivery and breakaway maneuvers above 6 weapon detonations ranging up to 5 megatons in yield. It is interesting to note the increased confidence of these crews on successive missions. On the first event, crew timing errors resulted in one aircraft being 2.5 times further away from ground zero than scheduled. On the second event, this error was cut to 7 seconds in time, or less than 1/10 of a nautical mile in distance. On the third event, the error was reduced to 2 seconds in time and a negligible amount in distance. During ensuing missions, each aircraft was at the assigned spot in time and distance. On Red Wing also, a research and development air crew accomplished the first delivery of a megaton bomb by a B-52 bomber. During the hardtack operation in 1958, the B-52 participated in 14 missions without blast or thermal damage. Significantly, the bulk of these missions were oriented to produce side-loading effects to determine the B-52's capability for multiple delivery strikes, where blast and thermal loads could be received at any angle from weapons delivered by other aircraft. Throughout the period of atomic testing, the hazard of nuclear radiation peculiar to fission and fusion weapons received a great deal of attention. Since delivery aircraft need to be concerned only with the nuclear cloud aspect of radiation, this report will be limited to the cloud studies. In the earlier operations, drone aircraft penetrations established safe parameters for the manned fly-throughs during Operation Teapot in 1955, when Air Force pilots flew T-33s through atomic clouds over Nevada 17 minutes after the burst. The first megaton cloud penetration study was made in 1956 on Operation Red Wing. Manned B-57s made 27 fly-throughs, the earliest 20 minutes after detonation. These test results formed the basis for the safe separation times listed in the EWO. Additional penetrations by B-57s during the 1958 hardtack operation verified the Red Wing conclusions. Throughout the years of nuclear testing, field operations were closely tied in with laboratory and aircraft plant activity. To gain vital time, much of the effects experimentation was first simulated in the plant workshops and research facilities before proof testing in the field. After each operation, findings were checked and cross-checked. Data on yields and distances from the bursts were projected into effects measurements on untried weapon yields, with results verified on ensuing operations. As experience and data were accumulated and methods were perfected, laboratory predictions became increasingly accurate. Thus, from the often lighted crucible of atomic test fire and attendant laboratory work, were collected the substantial array of results utilized to influence the planning of a safe route for you beyond the HHCL. This route planning, in turn, stems from a complex target assignment undertaking which began long before SAC headquarters issued its current EWO with your sortie number in it. When high-level target agreement has been reached, the Joint Chiefs of Staff assign SAC headquarters its quota of targets. Both targets and priorities are determined by national policy and the latest intelligence information. Shortly thereafter, the combat planners from the numbered air forces descend on Offutt Air Force Base to work out the target area allocations for each tactical unit. IBM computing units are utilized to work out this distribution, taking into consideration such factors as base location, type of aircraft, geographical area, and target priority. The next step, sortie-by-sortie detailed planning, is held at each numbered Air Force headquarters with representatives from each wing. While these men shape up the numerous requirements for each mission for the next EWO, they are fully aware that close by, in the command post, communications links to SAC headquarters and its worldwide network are under ceaseless scrutiny for the signal to execute the existing EWO. In the planning conference, each sortie is ground flown from takeoff to landing, its route dovetailing with that of every other mission. The nuclear test results are now applied to provide safe separation from other targets, as well as time separation from other detonations within target complex areas. The planners route you to obtain distance separation, or on rare occasions, change takeoff times to provide timing separation between bursts.
Well, how's it going? Sortie 1 is okay with the separation criteria that you've given to me. He can avoid this DGZ by breaking right after the target. We do have a problem with Sortie 2, however. He can avoid these DGZs by breaking left. But my performance engineer tells me that he will be out of fuel prior to reaching the post-strike phase. We've got to take him through this area somehow.
Yes, I remember this complex. As I recall, this is the last bomb down for option 1.
We'll have to keep track of the timing on this to make sure that it doesn't change in other options. Well, let's go over to my desk and check this out.
When all sortie planning throughout SAC is completed, the results are run through SAC headquarters IBM Center for a cross-check. It is during this runoff that precise weapon effects criteria and timing of all sorties are compared. Conflicts resulting from timing compression into the various launch options are adjusted. The final IBM runoff of the Annex F of the new EWO contains the exact target times for all launch options. The new EWO is now ready for adoption. In films, such as you are now viewing, as well as through specific briefings given you from time to time, you have been given an indication of how nuclear detonation effects concern you, the air crewman. For more detailed study, SAC's directives and manuals make this material available to you in various forms. All in all, the factors involved form an overwhelming mass of facts and figures. You cannot be expected to remember all the details, particularly beyond the HHCL, when you will be totally absorbed with the immediate pressing duties associated with your aircraft. So, it is reassuring to know that the documents in your combat mission folder stowed aboard your aircraft represent solid results based on countless man-hours of work done for you by the EWO planning personnel. For one never knows when.
Navigator, this is Pilot. Haven't we about reached the turnaround point? I'm about ready to head home.
Good timing. All set to change heading to standby 1. Something's coming in.
Sky King, this is Migrate. This is Migrate. Do not answer. Do not answer. Break. Break. Alpha Sierra Foxtrot. Bravo Juliet Oscar. Papa Mike Tango. Break. Go code. EW, check that authentication.
Pilot, this is EW. It checks.
We've received the gold code. Check your envelopes. Pilot to crew, we've checked the gold code and verified it. This is it. We're going in.
So you bore in past the HHCL. All 6 of you wrapped in this metal cocoon like a submarine crew beneath the sea. For the next few hours, except for the pilot's glimpse of the passing countryside during low-level operation, your only contact with the world outside will be a sporadic wink of light, followed by a sharp jolt.
Pilot, this is Neil over turning point number 12. Change heading to 061.
Roger, 061. Keep our course and timing right on the nose, boy.
That weapon from Blue Cell is about to go down on that government control center off the left. I hope he clobbers their fighter field too.
Roger. Guess that makes the war official, men. Keep those curtains buttoned up. We get a shock wave in a few minutes. That's it. Pilot to crew, report in.
Navigator to pilot. All instruments okay. Seem to be operating normally.
AW to pilot. Same here. Gunner to pilot. Sharp. Put an alarm down here.
Pilot, this is EW. I'm getting less GCI signals now. Pilot? Navigator. He said port coming up. I'm going to keep this bird clipping hedges. Just don't let your eyes off the panel. As soon as you see the flash, grab the controls, put us on instruments. I'll close the curtain and let you know how I am after I take off this patch. Roger, sir.
You've hit the IP on the button approaching your target.
Pilot, this is Nav. Up point in 5 seconds. 4, 3, 2, 1. On the way. Okay, take her up.
Now to get that separation distance between you and the bursts. You close your front curtain prior to the flash. The thermal heat builds up.
I have the crew clear for shock wave around.
Roger. All right, man. Brace yourself. On to all station. Give me a damage report.
Pilot, this is Nav. Signal right here. Radar 2.
Pilot from EW. I'm okay. Pilot from Tailgunner. Fine, here, sir.
Now to get back to altitude and start the long road back. It seems like the long way around to get to your post-strike base, but you remember working out an interference problem here. If you were to continue on this heading, it would place you within 7 nautical miles of the burst from a multi-megaton bomb scheduled about this time. You recall griping about your rerouting, particularly because this new heading takes you almost directly through the contaminated cloud of another bomb dropped 30 minutes ago. Like the rest of your crew, you are resigned to this lesser evil. From now on, the stage becomes less crowded as you move back toward the safe side of the HHCL. Yes, it could happen. If this nightmare situation ever materializes into grim reality, you may have a real bear by the tail. But at least, you are assured of escaping the nuclear effects of our own weapons. The years of testing and analysis have enabled SAC to evolve a workable plan for every sortie to and from the target area. You and each crewman of the Strategic Air Command can have this assurance as you rigidly follow your flight plan, especially the part marked beyond the HHCL.
Aviation, the art of aeronautics, began with the dreamers, inventors, and daredevils who dared to defy gravity. The journey of aviation was nurtured by pioneers like the Wright brothers, whose first flight marked a historic milestone. The role of aircrafts in world wars was groundbreaking, dramatically changing warfare strategies. This initiated a technological evolution in aviation, transforming the simplistic wings of a biplane into the thunderous roar of jet engines. Let's journey through the ages of aviation. Behind every great aircraft, there were great minds. These visionaries, like Sir Frank Whittle, the innovator of the turbojet engine, redefined air travel. Then there's Skunkworks' Kelly Johnson, the genius behind the SR-71 Blackbird. His designs combined speed, stealth, and power, crafting machines that dominated the heavens. The contributions of these pioneers have left an indelible mark on the canvas of aviation, shaping the course of history and inspiring generations of engineers and aviators. Each epoch in aviation history gave birth to extraordinary aircrafts, each with their own unique features and roles. The Lockheed SR-71 Blackbird was a marvel of speed and stealth. The F-105 Thunderchief, a supersonic fighter bomber, was vital in the Vietnam War. The P-51 Mustang, a long-range fighter, was critical in World War II. The P-47 Thunderbolt, a heavyweight fighter, was used extensively in the same war. The A-10 Thunderbolt II, the Warthog, is a close air support icon. The Messerschmitt Me-262 marked a leap forward in aviation technology. Each of these game changers were instrumental in their eras, and their legacies still resonate today. Beyond the game changers, there are those that have transcended their practical roles to become icons. The Concorde was not just an aircraft, it was a supersonic symbol of luxury and speed. The B-52 Stratofortress, a strategic bomber, is an icon of power and resilience. These magnificent machines and others like them have become much more than just aircrafts. They are enduring icons that encapsulate the audacious spirit, the relentless innovation, and the boundless ambition that define the world of aviation. For more amazing aerial footage, and to join us in this incredible journey, check out the DroneScapes YouTube channel.
If you enjoyed this video, please remember to like and subscribe. And as always, thank you for watching.